Hello students. Today's topic of discussion is a concept about solutions, how it is made, what is its composition, and few problems related with this. So we'll solve few of the numerical questions that are supposed to become in competitive exam, and we are also taking few examples from the previous years. It can be in any state, like it can be in the solid, liquid, or in the gaseous state. Okay, most of the time when we talk about the solution, we think of only liquid as a solvent. Okay, but it can be in the solid state also, can be in the gaseous state also, and obviously liquid is there. Similarly, this solute, which has a lesser percentage in the solution, is known as solute. So higher weightage is solvent, lower weightage in the solution is the solute. So even the solute can have the stages, it can be in the solid state, liquid state, or the gaseous state. Solubility is defined as the concentration of solute in a saturated solution. So what this saturated solution is? If you are adding solute to this solvent, you have taken the example of the solvent, suppose this is water, and you are adding one of the solid solute to it. For example, NaCl, suppose. Solvent is in the liquid state and the solute is in the solid state. So if you keep on adding this NaCl, there will be a time when it will stop dissolving into this solvent. So that point is known as the saturation. Okay, no further dissolution is taking place. So that will be the saturated solution. To increase the solubility of this thing, you can increase the temperature. If you increase the temperature, then the solubility of this water will increase and few more NaCl you can add into it and dissolve into it. Okay, if this is a solid state. So first we are taking the example of this solid. Then what if the solute is in the gaseous state? Suppose you are dissolving O2, oxygen, into water. Okay, so this is in gaseous state. In that case, if we'll increase the temperature, then the solubility of this oxygen gas will decrease. So what was happening in case of NaCl? If we are increasing the temperature, then the solid was dissolving more. Okay, but in case of gaseous solute, if we are increasing the temperature, then the solubility of this gas in water is decreasing. There will be few exceptions. We are also taking the examples of the exceptions. Suppose we have lithium carbonate. Okay, so we are dissolving lithium carbonate. This solute is in the solid state and the solvent is water. So this is exception. According to the theory that we have done now, if we are increasing the temperature, so solid solute, so dissolve more in water, but this is not dissolving more if you are increasing the temperature. So thing is, if you are increasing the temperature, solubility of lithium carbonate will decrease. So keep this thing in mind. There are a few exceptions to it also. Okay, same way there will be exception to this gaseous solute also. For example, if you are dissolving helium, so this is in the gaseous state and we are taking this as a solute. Okay, helium into water. What will happen if we increase the temperature? So in first instance, it will decrease. The solubility of helium will decrease a bit if we increase the temperature according to the law, because we have done, if you are dissolving in a gaseous solute and you are increasing the temperature, that time solubility will decrease. But this is an exception. First it will decrease with the rise in temperature. After that, its solubility will increase with the rise in temperature. So if you are increasing the temperature, then the solubility of helium initially will decrease, but after some time its solubility will start increasing. So these are the exceptions you have to keep in mind. Clear? Few more concepts to the solubility of solid and a gas in the liquid. So one law proposed by Henry proposed what it states: partial pressure is directly proportional to mole fraction. Okay, so if P is the partial pressure of gas over the solution, so we have dissolved some solute into it. Okay, now this is solution. There will be molecules of gaseous molecules over this solution, so it will be applying pressure on this solution. So individual molecules pressure will be there. So partial pressure of the gas over the solution in the vapor phase and the mole fraction of the gas. So here this is the mole fraction. So the partial pressure of a gas over the solution and the mole fraction of the same gas in the solution at a constant temperature, then these two are directly proportional. To remove this proportionality constant, now we're going to put a constant known as Henry constant. So this is partial pressure equal to Henry log constant into mole fraction. Now the value of KH, the value of this KH depends on nature of solute, solvent and temperature. The value of this KH, Henry log constant, depends on nature of solute, solvent and temperature. So if the solubility of a gas in the same liquid at the same temperature is S2, so there we get a relation S1 upon S2 will be equal to X1 upon X2. This X1, X2 are the mole fraction, equal to P1 upon P2. These two are the partial pressure. Okay, so this thing will be helpful in solving few of the numericals. So another law that we're going to discuss in the solution is the Rault's law. So in this case, the vapor pressure of liquid and the solid and liquid solution will consider. So let the partial vapor pressure of two volatile liquid is P1 and P2. The corresponding mole fractions are X1 and X2. So what's the relation? This P1 is directly proportional to mole fraction X1 and this P2 is directly proportional to X2 at equilibrium. So to remove this proportionality constant, so the equation will come out to be P1 equal to P1 naught X1. Okay, here P1 naught is a standard partial pressure. Okay, similarly here the P2 will be equal to P2 naught and X2. So this P1 and P2, it is the vapor pressure for pure liquids 1 and 2 when we have not added any solute to. Another law was given by Dalton. So according to him, P total will be equal to P1 plus P2. So from this equation, we can substitute the value of P1 and P2. So it's gonna look like X1 P1 naught plus X2 P2 naught. Okay, so P total is equal to this. So here the mole fraction, sum of the mole fraction as we know will be equal to 1. Sum of the mole fraction of the both the component will be equal to 1. So we can convert this X1 in term of X2 or X2 in term of X1. Hope all of you have understood it. Now one more concept. It is related with the ideal and non-ideal solution. So which type of solution is ideal and which type of solution is non-ideal. So ideal solution is a solution which obeys Rault's law over the entire range of the concentration. Okay, so the solution which obeys the Rault's law is known as ideal solution, and the solution which doesn't obey the Rault's law is non-ideal solution. So there are the few examples of the ideal solution and the non-ideal solution. So benzene plus toluene are ideal solution because these two obeys the Rault's law over the entire range of the concentration. For example, water and ethanol, non-ideal solutions. So with one example, we'll try to understand which sort of question they can ask from this topic. Benzene and naphthalene forms an ideal solution at the room temperature, C6H6, and this is C10H8. This is benzene and this is naphthalene, forming an ideal solution at room temperature. Which of the following thing will be true? Value of delta G is negative. Okay, so this is the first case. Second, delta S of the system is greater than 0 or positive. Delta S of the surrounding is equal to 0. And the fourth case, delta H is equal to 0. So for these two ideal solutions, in which one of the component is C6H6 benzene and another component is naphthalene, so which of the following is true? All of these options are correct. The value of Gibbs energy should be negative, delta S of the system should be positive, for the surrounding should be equal to 0, and delta H should be equal to 0. So if the solution is ideal, then this is the case. You can keep this thing in mind. It's a very important concept. Now we're gonna do the concept related with relative lowering of vapor pressure. This concept in the solution chapter is very important. Standard pressure of the pure solvent minus the pressure of the solution. So this is equal to mole fraction of the solute. So we can write this this equation as this also. X2 can be written as number of mole of solute on number of mole of solvent plus number of mole of solute. Here the P1 naught is the vapor pressure of pure solvent. P1 is the vapor pressure of solution after putting the solute into it. N1, N2 are the respective mole fraction of solvent and solute. This is of the solvent and this is of solute. If the solution, this is true, and if the solution is very dilute, that time the value of N1 is much greater than N2. Okay, when the solution is very dilute. And now the equation, we can write this thing simply as these two will be the same. We can write this as, because the value of this N2 is negligible in comparison to N1. Now one more concept related with this. What if this is not very dilute? Then this formula will look like P1 naught minus P1 and divided by P1. So here we have taken the pressure of the pure solvent, but here we'll take the pressure of solution. Okay, this will be equal to N2 upon N1. Keep this in mind. So when this is the situation, when there is a change in this denominator part, when it is not very dilute. If this is very dilute, then this is the case. So only changes this part. So while doing the question, you have to read the question carefully. Now we are doing some more concept. So one is elevation of boiling point. What if we add some solute to the solvent, then there will be increase in its boiling point. So how are we gonna express this concept? So the change in boiling point will express this as delta TB. This delta TB is change in boiling point. So final boiling point of the solution is this minus boiling point of pure solvent. Okay, so the initially the boiling point was less. When we added some solute to it, then solution's boiling point increases. So difference is delta TB. Okay, so what's the relationship between this change in boiling point and the molality? Change in boiling point is directly proportional to molality. Okay, so this molality is, if you don't know, this molality is number of solute divided by mass of solvent in kg. So this elevation in boiling point is directly proportional to this molality. So we'll remove this proportionality Kb. Kb is known as elevation constant or ebullioscopic constant. So now what will be the question? They can ask the numerical based on this, and then numerical will be to find the molecular weight. Another question in MCQ, they can ask you what is the unit of this Kb, elevation in boiling point. So it is Kelvin kg per mole, okay, or mole inverse. One more formula related to Kb. So we can find Kb by this method also. So here this L is latent heat of vaporization. Now similarly we'll have the depression in freezing point. So if we'll add some solute to the pure solvent, then its freezing point will decrease. So suppose for pure solvent freezing point is delta Tf, and for solution it is Tf. Okay, so what will be the change? This change, because it is depression in freezing point, so initial minus final. Okay, by adding some solute, its freezing point has decreased. Now again, same way, this delta Tf is directly proportional to molality, and we can write this as this Kf is depression constant or cryoscopic constant. The unit for this will be Kelvin kg per mole. We can find delta Kf, okay, cryoscopic constant. So this is latent heat of fusion of solvent. Clear? Few more concepts related with the osmosis and osmotic pressure. So what this osmosis is? Process of flow of solvent. This solvent is at lower concentration. Process of flow of solvent from lower concentration to solution. This is at higher concentration. Okay. So what we are doing? We are doing osmosis. So the process of flow of solvent to the solution through a semi-permeable membrane. So there is a membrane, it is SPM, semi-permeable, okay, is known as osmosis. It is a spontaneous and no external energy source is required. So again I am repeating, the process of flow of solvent to the solution through a semi-permeable membrane is known as osmosis, and it is a spontaneous and no external energy sources required. Then comes reverse osmosis, RO, reverse osmosis. So if we apply extra pressure on the solution side, so this is a solution side, if you're gonna put extra pressure on the solution side such that the natural flow is reversed. So this was the flow in case of osmosis. Now the natural flow will be reversed. So if we'll apply extra pressure in the solution side, so solvent from this side will start moving into the opposite direction to the pure solvent side. So if we'll apply extra pressure on the solution side such that natural flow is reversed, that is flow of solvent from the solution to the pure solvent side is known as reverse osmosis. Now what's the osmotic pressure? If the applied pressure in the above case, if this is the applied pressure, is such that it stops the natural flow of solvent due to osmosis. So naturally it was going from this side to this side, and if you apply the pressure and it stops this flow, okay, now solvent stops going from this side to this side, just is stopped, then this pressure is known as osmotic pressure. So see, here is the molarity of the solution. So pi is directly proportional to C, or we can write it osmotic pressure is equal to. Now one more concept about this that you have to keep in mind. As I told, in osmosis pure solvent naturally will move from lower concentration to higher concentration solution side. So this process is in the both the direction. Osmosis the solvent flow in the both the direction. Okay, so both the way it is going. But thing is, net flow is from low concentration to high concentration. If they ask you during the osmosis, flow of water through a SPM is from both the side of semi-permeable membrane with unequal flow rate. So it is from both the side with unequal rate. And net flow when is towards the right hand side, toward the solution side, from lower concentration to higher concentration, then it is known as osmosis. Now, one more concept related with Van-Hoff factor. So this I is what? So Van-Hoff factor I is experimental colligative property upon theoretical colligative property, or in another way you can say it is theoretical molar mass upon experimental molar mass. So what if the value of I is equal to 1? It means the solute is not dissociating or associating properly, then this is I equal to 1. So when the value of this Van-Hoff factor is 1, it means solute is not dissociating or associating properly. If this value of I is greater than 1, so solute dissociates, and if the value of I is less than 1, then the solute associates. And how to find the formula is there, but while solving some of the numerical, you can apply this trick. If the solute is NaCl, so Van-Hoff factor for this solute will be equal to 2. How? Number of ions you have to think of. If they are saying it is a completely associating or completely dissociating, so number of ions 2, so value for I will be equal to 2. Similarly, like some other solute, if there is, so number of ions in this case, or cations, 2, and anions 1. So the value for I will be equal to 3. So few more examples and all I will do in coming videos related with this chapter.